Hello, and welcome to the next, latest, and greatest. I'm calling it code review slash textbook review of Java Illuminated, 5th edition. And yeah, I want to go over a lot of the code that is presented in this book because I am a big believer in that you need to be able to read code before you can write code. And so, as long as we can go over these examples and understand them, you should have the fundamentals necessary to kind of start writing code on your own. Okay. And so, I'm not trying to replace the textbook at all. In fact, I'm trying to provide feedback to the publisher. I'm trying to connect all the dots so that we can really dive into code. I love code. I love talking about code. Okay. And the last code review video, I think I got up to, yeah, it looks like 2.5. And so that's kind of where I want to begin here is let's start looking at those examples in chapter 2, starting at example 2.7. And if anything gets too complicated, I'll reference you back to the book as far as where that, excuse me, particular concept is called out. Okay. So yeah, they give us this example here called division and modulus, and this is definitely one of the areas where a lot of students struggle is with something called the modulus operator. But it is a very powerful operator and enables us to obtain the remainder of a division problem. And a lot of times we need to know that in the real world, right? Well, it's easy to get the whole number. We just divide the numerator by the denominator, and we can see how many whole number of times that the numerator goes into the denominator. But then the question is, well, how many is remaining if we don't want the decimal, right? If we don't want the decimal, sometimes you want to know, well, how many is remaining? And that's what this example is going to show us. But let's look at it at a high level real quick, and then let's step through it with the debugger and make sure that it is behaving and doing everything we expect. All right, so the first thing we're going to notice is, yeah, we've got a public class, right? Every Java program requires you to have at least one public class with a public static void main method. And if you remember from the previous code review slash webinar, um, every program, right, starts with main. Um, and I go over why these curly brackets are necessary in previous code review, but they define scope for Java and other languages. Basically, this is letting us know that this public class starts here on line 6 and ends here on line 26. So everything in between these curly brackets here is part of this public class called division and modulus. And then for public static void main, again, we need to define the scope of main, and that's what this open curly bracket is here, and this closed curly bracket is here. Everything in between these two curly brackets is part of this method called main. So when we launch the application, it should look for main. It should go to the very first line of code in main, which is line 9 here. And it looks like and we talked about this last webinar, we are declaring what's called a constant. And how do we know it's a constant? We have this keyword here called final, and it basically means that whatever value is inside of this variable here, we can't change it. And it makes sense, right? Pennies per quarter, well, yeah, there's 25 pennies in each quarter, so that's not going to change, right? Unless the US currency system changes, I guess. All right. So for sure it's equal to 25. And because this is a constant, we name this variable in all caps. That's just good programming practice, and it lets other software engineers know that look at your code. All right, this is a constant variable. I can't change it. All right, and then line 10 says, all right, we've got a variable called pennies that we set to 113. That's kind of a random value. Not sure why they picked that number, but whatever. This is our input, right? For sure, every program fits the IPO paradigm. What they're doing is they're initializing our input and our constants here at the top. All right, so then we get down here to line 14, and it looks like we're going to take whatever the value inside of pennies is, and we're going to divide it by pennies per quarter. So why would we do that? In order to obtain the total number of quarters, right, that we need if we're given this many pennies, and that seems to make sense. Um, and notice that everything is an int here. And that is intentional because if we divide an int by an int, it's going to give us an int. Even though there may be, right, 113 divided by 25 might have a decimal in it, but we don't care about the decimal. We're just asking for the whole number of quarters. So I believe they intentionally utilize an integer data type here so that the quarters won't have a decimal point in it. And the other part I'd like to point out is this is, right, IPO paradigm. This is the process part of the algorithm, right? This is why we created the algorithm, is to do the math for us, all right? And what else we got here? Aha, we've got a print line statement. So that looks like the output to me, and it's going to let us know, well, if we have this many quarters. This many quarters exists using this many pennies. All right, so it's going to do the conversion for us and let us know how many quarters are there. And then it looks like we're going to do a little more processing of the data here. So this part of the process lets us know how many whole quarters. This part of the process looks like we're going to be calculating pennies left over, right? So, well, that's fine. You've got this many quarters, but we're going to have some pennies left over. And this is the infamous modulus operator. This is kind of the whole point of this example. We use a percent sign here, and for a lot of students who are new to programming, they assume this percent means the same thing like the percent sign in the real world, right? When you see a percent, you go, okay, well, that's a percentage from 1 to 100 that represents a percentage, I guess, right? But here, and I would say at least most programming languages, the percent sign actually means modulus. And when we do modulus, what that means is, okay, take pennies, divide it by this variable here, pennies per quarter, and whatever remainder is left over, that's what this modulus operator is going to return, right? So for instance, if we take 113 divided by 25, well, for sure, 4 quarters will go into 113, right? And that equals 100. But there's still 13 pennies left over, right? So this modulus operator under this condition here should return 13, and this is the assignment operator. So we're going to take 13 and we're going to plug it into the variable here called pennies left over on the left-hand side. Also note that, yeah, we don't have to declare all of our variables at the top of the method. Some older languages do enforce that, but at least for Java, you can declare a variable when you need it. It doesn't have to be at the top. All right, so that's another interesting observation. Then here, underneath the second process, we have a second output, right, where we're going to call out how many pennies are left over after we convert the other pennies to quarters, right? And that's the whole point of this line here, is to show us how many pennies are left over. And then finally, oh wow, look at this. They're declaring constants down below now too. They're kind of all over the place. I really, my preference here would be, and I guess they're trying to, okay, they're trying to group this stuff together. Obviously, we're talking about annual salary and months per year here at the bottom. That's separate from pennies and quarters, so I think that's why they declared these variables down here. All right. And this is almost like two little mini programs. Probably better practice once we get to learn how to create methods would be to break, this part of the code up into one method and this part of the code up into a second method. All right, because every method should do one thing well. Okay, so we're declaring variables. We have a constant called months per year that we're going to set to 12. We've got an annual salary that is a double or includes a decimal point here declared. It looks like 50,000. And then what are we going to do here? We're going to take the annual salary, divide it by 12. Now notice here, everything is a double. Up here, everything was an int. So here, If you want to use it, if you want the output to contain a decimal point instead of a remainder, well, then just declare everything as a double or a float, and the compiler sees double divided by double. It's going to give us a double, okay, and then it's going to assign it to this variable here called monthly salary and process output. So we got several processes that right processes going on here, and several outputs. All right, and then it's basically going to let us know what the monthly salary is. So let's launch the debugger, right? Let's put a breakpoint here on line 10 by clicking on this number 10 here. And again, I'm using NetBeans. There's lots of other Java IDEs out there, but they all should, if they're good IDE, contain a debugger. You should be able to set a breakpoint. And we want to, walk through this and verify its behavior. So that's what I'm going to do right here. I'm going to start the debugger. Okay, division modulus, that's fine. You can do this, or you can right click and say debug file. Either one's fine. All right, so here, and I kind of like having I'm not going to lie, the variables window over here. All right, so this is what's basically declared in memory. All right, at least the variables that are declared in memory. And for this particular application. So we start at line 10. Notice the program counter did stop at line 10 because we put that breakpoint there. And this first line here should declare a constant variable called pennies per quarter equal to, it set it equal to 25. So when I click step over here on line 10, we should see, right, pennies per quarter set to 25. Next line, create another variable called pennies, right, line 12. Set to 113. So when I click step over here, I would expect to see, right, this pennies set to 113 over here, and it does. Let's look at line 15. All right, it's going to take whatever's in pennies. And notice that this IDE, if you hover over these variable names, it shows you exactly, right, what value is inside of each one of these variables. And that comes in very handy later on, especially if you have a big complex program and you're in the middle of a bunch of loops. So you can either hover over it and see it, or you can come over here and see the values. All right. But here we're going to take 113 divided by 25. That should be 4 point something. But because we're doing int, it's going to drop off the point something, right? And it's just going to be, should just be 4. I would expect to see the value 4. Create a variable here called quarters with the value 4 when I step over here, and it does. So that makes sense. Line 17, okay, let's print out what's in quarters, which is 4, what's in pennies, which is 113, along with these strings. And this plus operator here is known as a concatenator. Okay, say that 10 times fast. And it basically joins, it converts these numerical values to a string, and it appends all of these strings together onto one line. And so on the output here, I would expect to see there are 4 quarters and 113 pennies, and we do. Line 21 says, all right, well, let's take this number of pennies and let's run the modulus operator, right? So what is 113 modulus 25? Well, that's 113 divided by 25, which is 4, but the remainder is 13, right? 25 times 4 is 100. 113 minus 100 is 13. So when I hit step over here, I would expect to see a new variable over here called pennies left over set to 13. And it is because of the modulus. All right, and then line 23 says, all right, well, let's print out some output. Here's some strings, and let's go ahead and let the user know what values inside of pennies left over, which in this case is 13. Yep, that looks good to me. And then we get down here to line 27, declare a new constant called months per year. So I'd expect to see that appear over here, and we do. Another variable called annual salary that is not a constant, that is a double. It's equal to 50,000. So when I hit step over here, I'd expect to see it here. All right. And then we get down to line 31. All right, here's the monthly salary divided by annual salary equals, sorry, annual salary divided by months per year. I don't know, 50,000 divided by 12, a lot of math. I'm going to have to, let's hit step over here. I mean, I don't know, let's say 10. Annual salary divided by 10 would be 5,000. So somewhere around 5,000 is what we would expect to see in this monthly salary, maybe a little bit less. All right, so let's step over here. Yeah, around 4,100-ish. All right, so that looks good. And then the last line here, let's print out whatever is inside of this monthly salary variable, the monthly salary is, and I would expect to see that down here. And we do. So that looks good to me. Yeah, the output's a little wonky, right? I don't, a lot of decimal places here. There are ways to format what the string looks like, especially if it has decimal points in it, but that's later. All right, we're not going to talk about that just yet. All right, so, and then we're at the last line. How do we know that? Because we've reached the last curly bracket. So when I click on step over, it should just terminate. The application is done and everybody's happy. All right, so this example really showed us how to use a modulus operator and one real world reason why that might come in handy. And there are plenty of others. All right, so enough about that. That is example 2.7. Let's look at, what's this, example 2.8. Ah, yes, the infamous divide by zero. So, computers are logical machines. They have an ALU, or an arithmetic logic unit, and they have a control unit. And when you try to tell the ALU to divide by zero, and even in math class, well, in math class we're taught if you divide by zero, even in math class we're taught that's not possible. All right, so for sure we can't divide by zero, and that is what this particular example here is trying to show us. But just high level, go over it, and then we'll walk through it. Yeah, we got this class called division by zero. It's public, right? We have to have a public class with a public static void main. It's here. We have the proper curly brackets for main. We have the proper curly brackets for division by zero. All right, so that makes sense. Here, declaring a variable called result1 equals 4.3 divided by 0. That's can't do that, right? So it'll be interesting to see, right, what the computer will do about this. It might crash. It might print out an error. This is why we need the debugger. This is why we need to tell the computer to execute each line of code one at a time, because right now, I would say each computer and each programming language reacts a little bit differently to divide by zero, but definitely it's not a good thing. And in industry, you never want to divide by zero, which means that you should do what's called input validation. Before you run these equations with the denominator, make sure above all this, you're checking to see, is that denominator equal to zero? And if so, you don't try to do this. Hackers love this. Hackers love programs that where you don't do input validation, because if this were a variable instead of a hard-coded zero, what they would do is they would try to send in the value zero into the variable and see, right? And see if the program blows up. That's what hackers love to do. Okay, so ultimately later on, once we learn about conditional logic, we'll see that we can do some input validation, but we don't know about that yet. So here we're going to do a science experiment, try to divide by zero. Here it looks like we're going to try to do the same science experiment with zero on top and bottom. It'll be interesting to see what comes back there. And then here, instead of using doubles, right, or floating point values, we're going to try to use two integers. But one of the integers is zero in the denominator. I've seen, anyways. Long story short is I'm not sure what this is going to do, so I'm going to set a breakpoint on line 9, and we are going to run the debugger, and let's see what happens. Wait, excuse me, debug file. So I'm running the debugger. I hit debug file, and we're on line 9 here. And the question is, well, if I hit step over, well, what do I expect to see in memory? Well, for sure, it should declare this variable called result1. but I have no idea what value it's going to produce here. So I'm just going to go ahead and click on step over here. Here's result one, result one. Ooh, interesting. So the value that it returns is a value called infinity, which is interesting. So apparently if you have a double, at least in the Java environment, and that kind of makes sense, right? 4.3 divided by 0, well, 0 will go into 4.3 infinite number of times. So yeah, okay, fair enough. Infinity does sound right. And in line 10 is going to print out, right, print line, the string plus the result. So I'd expect to see that down here in the output window. Let's hit step over. The result, the value of result one is infinity. All right, fair enough. We get to line 13 here. Well, is this going to result in infinity as well? Well, it's kind of different, right? 0 divided by 0 should be just 0, theoretically. Let's see what happens. Let's step over line 12. NaN. And I don't even know what that stands for. I have to look that up. NaN. Here, give me just a second. Yeah, now this is funny. This is funny. So these computer scientists, they create acronyms for everything. So I just looked it up. NaN means not a number. Why not just put not a number? Why you got to leave us guessing? Whatever. All right, so you can't do this, and if you try to do this, then you're going to get something like this with an NaN return value. And at the end of the day, look at industry, we're never going to do this, right? We're always going to look to see, is the denominator 0? And if so, well, then we're just not going to try this math. All right, but I guess here in this example, they're trying to show you what would happen if you did try to divide by 0. Okay. And then, yeah, we step over that. It shows us the result 2 is equal to NaN. And then we get to line 15 here, and it says, okay, well, let's try this. 4 divided by 0. Both are integers. All right. I don't know. Maybe we get a NaN int. Who knows? And when we hit step over here, in fact, what happens is that it throws an exception. So if we, let me show you. The computer is able to handle some of these cases without blowing up or without throwing an exception. However, with when you try to divide, apparently when you try to divide by 0 with an integer, I guess that's just crossing the line. Like with 0.0, they're like, yeah, infinity, yeah, man. And then you try to do it with a integer at 0, and it's like, mind blown. All right. So this just highlights the importance of doing input validation and making sure that you don't try to divide by 0, especially if it's an int. Because if it is, it's going to throw an exception. And if you're not catching that exception, yeah, the whole thing's going to go kaboom. But later on, we will learn about exceptions. There is a way to catch the exception that this throws, and we could just print out here. The title of the exception is slash by 0 or divide by 0. So up here, they return the error result in the actual result itself. Here, they throw an exception. So long story short, just don't divide by 0. And you don't have to worry about any of this. Just do input validation before you go to try to use whatever that value is in the denominator. Make sure it's not 0. All right. Okay. So that is example 2.8. Let's move on, shall we? Maybe we can get through chapter 2 today. It would be amazing. All right. Example 2.9. Example 2.9, shortcut operators. Another brilliant idea. Notice the sarcasm by previous computer scientists. And it does have its uses. They're very niche, but let's talk about this. High level public class called shortcut operators with a public static void main. So we're set up nicely to create the application. We have the proper open close curly brackets, open close curly brackets for main and the class. That all looks good. Looks like we're declaring variables, right? In fact, it looks like this is the input. Okay, so A is equal to 6, B is equal to 2. Terrible variable names, but whatever. All right, A is equal to 6, B is equal to 2. They're just two random values. Now here, they're demonstrating the shortcut operator. What the heck is a shortcut operator? Well, for line 13, we're used to this. Here's a print line, string plus A, which means that we're going to convert A to a string, and we're going to append it to this string. No big deal. However, if we look at line 14, we see this plus plus A guy in front of or behind this plus operator. What in the heck is that? This plus plus in front of the A is what's called the shortcut operator. And it basically just means when you see, let's talk at a high level for a second. Plus plus A or B plus plus, somebody got lazy and they didn't want to type this at a high level. All right. Plus plus A is the same as A equals A plus 1. So if A is equal to 6 here, right? All right, it'll come down here. 6 plus 1 is 7, and it's going to assign the value 7 to A. So we're basically incrementing by 1 using plus plus A. So then the question is, well, if that's all we're doing, and that does the same thing, why is this in front of the variable and this is behind the variable? Aha, glad you asked. Well, again, somebody at some point in the land of computer science said, well, how cool would it be if we had this shortcut operator, and if it was in front of it, we would do that calculation before any of the rest of the code, before we execute any of the rest of the code that's on that line, we do this first. But here, if we put the plus plus behind, or the shortcut operator behind the variable, we execute this line of code first, and then we increment B by 1. So notice how confusing this can get, right? I mean, to me, if you want to increment A by 1, and you know, some old school programmers are laughing at me right now, just do that on the line before this and get rid of that. Call me crazy. If you want to increment B after this line of code, right, just do this, right? Call it a day. This is much more readable than this, but again, old school programmers, they've been doing this forever, and they're like, noob. But again, we want good readable code. These variable names are terrible. These post and pre and post shortcut operators, to me, are just, it comes from old C style programming, but I don't want to go there. All right, so that's all they're trying to show us here, is that we've got this plus plus guy, these shortcut operators, pre and post increment operators, and I think that's called out in your book, just in case it is a little confusing, which, yeah, it is a little confusing in the beginning. Where is it? I could have swore that arithmetic operators, I believe it's somewhere in here. We should see the pre and the post. Give me a second. Yeah, they call that out here in 2.3.8. And they kind of show you the different ways. Okay, so for sure it is in the textbook there at 2.3.8. But enough about this. Obviously, and these lines, look, we're combining the process and the output all into kind of one line of code, and of course you can do that, but we're kind of mixing things. And in the beginning, at least when you're first learning how to program, I wish they would separate the process and the output. But eventually, when you get to industry, you do need to know how to combine them. All right, let's go ahead and set a breakpoint here. Let's see what this does. This is exciting, right? So we think we know what's going to happen. Let's see if it actually happens. All right, line 10, I'm going to create a variable called A over here, set it to 6. And it does. Line 11 is going to create a variable, integer variable called b, set it to the value 2, and it does. 14 is going to print this string with whatever a is converted to a string, which is 6. We should see that down here in the output window. At the beginning, a is 6. That looks good. Aha. Line 15. This is the line of code in question. What is this plus plus a going to do? Well, if it executes plus plus before the print line, a is 6, it should say incremental with prefix notation and the number 7. If it executes plus plus after print line, then we're going to see the number 6. All right, so let's see what happens here. Yeah, it's the number 7 because it's a prefix operation. All right, so if it's in the front, it does this first, and then it does the print line. All right, and in line 16 says in the end a is blah, and it remains 7. Why? Because it incremented it before it showed us on line 15. Now, a little bit different situation here on line 19, right? Well, at the beginning, b is, well, probably 2. We should see at the beginning b is 2. All right. And then increment b with postfix. So notice the plus plus is after b. So it's going to run this print line statement first and print out the current version of b, which is 2. But then as soon as it executes this print line statement, it's going to increment b to 3. And we should see 3 on this line of code here. So I would expect line 20 here to show me the value 2. And then under the hood, like as soon as you hit step over, it incremented it to 3. But look, here in the output, what you see is 2 because this is the postfix. It executes this after the line of code that it belongs to. And then finally on line 20, okay, now let's print out B. Now let's print out B, and at this point we should see the value number 3. Okay, so notice prefix shortcut operator incremented it before it was printed out. Postfix operator doesn't increment it until after that entire line of code has been executed. All right, so, and I will say this, when we get into loops later on and we need to increment a counter for our loops, yeah, you're going to see this a lot. Well, actually, you see this one more than this one, but we are going to see some shortcut operators, especially when we're creating counting loops. But let's worry about that later on. And then I hit step over here, application's done, program terminates. All right, all right. Let's go to, what is this, example 210. Well, looky here. So we have some more shortcut operators. They're a little bit different. High level, this program looks good, right? We got a public class. We've got a public static void main. Inside of the public class, we've got the proper open, close, curly brackets. Notice what happens if we try to remove one of these. You get an error in your code. That's why I'm always verifying, the framework first before I start to dig into the code. And a lot of students who are new to programming, right, they forget one of these and then they freak out, right? So always, verify that your class declaration and your curly brackets and your method, your main method and your curly brackets is all defined well before you come in here and start writing code. All right, well, what else? And again, we're reading code and then eventually we'll start to write code. Okay, first line, create a variable a equal to 5. No problem. Next line, we'll print out what a is currently equal to. No problem. Next line, a plus equal 10. What in the heck is that? So again, programmers got lazy in the past. And this is the same thing as this. You're just adding 10 to whatever a is, and then you're putting that result back into a. Okay? A minus equal 3 is equal to A equals A minus 3. So again, take away 3 from A and put the result into A. So it's just kind of shorthand notation, right? If we have these variables and we want to add or subtract or multiply, and we want the result to go back into the original variable, then we utilize these shortcut operators. Now, let's see if they really work. Let's put a breakpoint here on line 9. Let's debug the file. All right. Line 9, create a variable called a equal to 5 over here. Looks good, is an integer. Print out what a is equal to. Let's look at the output window. A is 5. A is 5. Makes sense. That looks good. All right, line 12. A plus equal to 10. Well, in my head, I'm going, all right, what should the behavior of this line be? Well, if A is 5, this basically means A is equal to 5 plus 10. Right? 5 plus 10 is 15. It's going to take the 15 and put it back into A. So when I hit step over here on 12, I would expect A to be set to 15. And it is. All right. And then we're going to print out that current version of A, which is 15 to the output. That looks good. Line 15, minus equal 3. Well, A is currently, what, 15, right? 15 minus 3 is 12. So when I step over this, we should see A go to 12. And we do. And then we're going to print that out to the screen. We see that here. And then line 18, all right, A times equal to. Remember, the asterisk is multiply. Well, that would mean A is equal to 12 times 2. I believe that to be 24. So we should see the value 24 get put into A here. 24. Let me hit step over. We do. And then we're going to print out that value down below. And that's good. And then A equals A divided by 6. So 24 divided by 6, what is that, 4? So we should see the value 4 go into A here. So when I step over 21, I should see the value 4. We do. And then we print that out to the screen with line 22. And 24, line 24, A equals A modulus 3. Ooh. All right. Well, A is currently 4. 4 modulus 3. What the heck is that? Well, 4 divided by 3 is 1, right? 3 will go into 4 one time with the remainder of 1, right? 4 divided by 3 is 1, remainder 1. And so this is going to return the value 1 because the remainder is 1. So A is going to equal 1 at this point. So when we click on step over here on line 24, I would expect to see A equal to 1 here, and we do, and then we print it out to the screen, and we see that down here. So all that looks good to me. It all behaves well. Click on step over on this last curly bracket here, and the program terminates or finishes. Okay, what else? What else? What else? Ooh, look, we're almost there. Let's go over participation activity 1 in the book. And yeah, let's take a look at that. And these participation activities are really good practice, in fact. What they do is they present you a problem in the book, and I do really like this, note to publisher, and they will ask you to do something, right? And they will give you basically a starter Java definition, class definition, and then they put in some high-level pseudocode or high-level statements here, and they expect you to be able to convert this into Java. And so this is where we're kind of trying to write code once we're able to read all the previous examples. And for this particular participation activity, let's make sure we understand why the solution is what it is. All right. For instance, within this public class called metric length, which has a main method, we do have two. Well, now didn't the previous examples use curly brackets on their own line? Sure did. In industry, this is my preference for sure. Curly brackets on their own line, and it's really easy to see which curly bracket lines up with the other. Some people do this, but the problem is when I come down here and I go to line this up, I'm not seeing that open curly bracket. You have to go all the way to the end of this line. And I think that this is just much more readable, but I don't know. Yes, 10 different programmers, 5 of them will say one way, the other 5 say the other way. But definitely the indentation needs to be proper. And the indentation here looks good. It's just they wanted to put their curly brackets on the end here instead of right underneath. All right, so first part here asks us what data values do we know? Oh, I guess they give us a high-level problem. Let's read the high-level problem first. High-level problem says we need to create a program called metric length. All right. And this is an example of the output. So many inches are equivalent to so many centimeters. So that's kind of the whole point of this program here, is to convert inches to centimeters. All right, well, for sure we do have a constant. There is definitely 2.54 centimeters in every inch. And so we can go ahead and declare this constant variable here as a double, right? Has a decimal point in it, and make sure it's final, because that's never going to change, right? I guess if time and space are warped, but we won't talk about that. All right, so that makes sense. Then line 22, we declare inches. So I guess this is the number of inches that the user wants to convert to centimeters. And it's kind of out of nowhere. I don't think the book tells us 10 anywhere here. So we're just kind of picking a random value. So we picked 10. And we're going to learn later on how the user can enter this information in at runtime. But right now we don't know about that. So we're constantly hard coding our input into the actual program itself. And then let's see, section 3 here. Well, let's do the process, right? So this is the input. Here's the process. Let's convert inches into centimeters, and the way we can do that, well, if 1 inch is equal to 2.54 centimeters, well, then we just take the number of inches times the centimeters per inch constant, and bada boom, bada bang, right? That should give us the total number of centimeters as a double. Once we have that, right, input, process, output, then we're going to go ahead and print out to the screen what that centimeters variable is equal to. Well, let's see it in action. I'm going to put a breakpoint on the first line of code here in main. I'm going to launch well, let me close this one so I don't get confused. Launch the debugger. So I would expect line 15 to create a variable over here and set it to 2.54 called centimeters per inch. Looks good. Notice that it skips over, right? The debugger and the computer skip over all of this. These are called comments. This is a multi-line comment. All right, multi-line comments start with /* and they end with // and the computer ignores everything in between the /* and the //. These comments here are for the humans. All right, so when we started the debugger here and we hit step over, it jumps down here to line 22 because that is the next line of code, right? It has nothing to do with any of this. So line 22 says, okay, create this variable called inches, set it to equal to 10. We should see that over here. We do. And then line 29 says, all right, create a variable called centimeters. Aha. But first, do this calculation. Inches times centimeters per inch. Well, inches is currently 10, right? Centimeters per inch is 2.54. Therefore, 10 times 2.54 is 25.4, right? We just moved the decimal over 1. 25.4. So when I hit step over here, we should see centimeters equal to 25.4 over here. And we do, so that makes sense. And in line 36 is we'll print out, right? The number of inches is blah, centimeters, we should see that down here in the output window. And we do. And then finally, we're at the end of the program, hit step over, and it terminates. So makes sense to me, at least this is converting 10 inches for us. If we wanted to do 20, well, guess what? We could change that to 20 And then we could run that, and we could see what 20 is equal to. We want 50. We could run this, right, and see what 50 is equal to. All right. So that is participation activity 1. Let's take a look at participation activity 2. All right. And here, all right, what do they want us to do? Let's look at that first. Oh, right, temperature conversion. So here, a lot of students get a little nervous about math when they're presented with these formulas. But the key to this formula here, and what a lot of students don't realize, is this 5/9, and then there's parentheses here. In algebra, it's implied that there's a multiplication symbol here. This is 5/9 times Fahrenheit minus 32 in parentheses. So there is a hidden multiplication operator here that we need to use in order to get from Fahrenheit to Celsius. And then if you look at the statements, it also looks like they want us to go from Celsius back to Fahrenheit, and they give us this equation here, and at least here they're showing us the multiplication going on, but for some reason they withhold the parentheses, but maybe that's intentional. Yeah, maybe you need to do this first and then add 32. So those are the two formulas. We're just converting from, Celsius to Fahrenheit and Fahrenheit to Celsius. So they ask us to declare any constants. Well, for sure, and they don't really call that out here, but 32 is the freezing point of water. That's not going to change. So yeah, this is a good candidate for a constant. So that's why that's declared as the final, and we're setting it equal to 32. It is an integer. Guess to be precise, we could declare it as a double and put a 0.0 there. But that makes sense there. Line 2, declare temperature in Fahrenheit as an int, which is a bit odd. I would think you'd want to declare it as a double, but whatever. Okay, so here's Fahrenheit. We set it equal to, and it doesn't tell us what value. We can pick any value, but here I picked 68. And then line 15 says we'll calculate the equivalent Celsius temperature, I assume from Fahrenheit. So that's where we have to use the 5 divided by 9, all right, times the Fahrenheit value minus freezing point. And again, that is the formula here. All right. Notice though, the 9 here is an integer. Here though, all of a sudden there's a 0.0, and there is definitely a reason for that. Remember when we were talking earlier, if we do an int divided by an int, and it has a decimal in it, the result, it's going to drop that decimal. Well, that's a problem here, right? Because 5/9, 5 divided by 9 is 0 point something, right? It's a small value. It's 0 point something. And if we drop the point something, this is just equal to 0, because this is an int divided by an int. This is going to equal 0, and this whole thing is going to equal 0. And in fact, I'll show you that here in just a second. And that's why we add this dot 0, so we can get a much more precise value here. And we'll do a little science experiment in a second. I'll show you that. Let's see, line 4, output the temperature in Celsius. Yeah, well, here's your Fahrenheit, right? There's your Fahrenheit temperature. Here's your Celsius resultant temperature. And let's print that out to the screen. And then line 23 says, all right, well, let's go back the other way. So the thing is, though, we're not really going to know if this, let's modify this a little bit. We'll let this call this Fahrenheit, but here, let's call this int Fahrenheit 2. And the reason is that I want to know that Fahrenheit 2 is equal to the original Fahrenheit, right? If we just let it be equal, overwrite the original Fahrenheit, well, we're not really going to have anything to compare this Fahrenheit value to the original. So let's go ahead and declare a new variable called Fahrenheit 2 and output that and make sure that that is equal to the original value. All right, so let's set a breakpoint here. Let's step through it. Let's make sure that it's doing what it's supposed to do. All right, and we hit line 10. Yep, here's a freezing point variable called with value 32. That is a constant. That's here. We hit line 12. All right, well, here's another variable called Fahrenheit that is set to 68. That is an integer, so that makes sense. Line 15. All right, well, here's where we've got to do math. And I don't know, 68 seems to be, if I remember correctly, around 20 degrees Celsius. Um, whatever 68 minus 32 is, and then you got to multiply it by this 5 divided by 9. So let's just hit step over here. I guess to be really precise, to be really sure, you could break out a calculator and do this on a calculator, and then we'll look for that value. So I'm going to step over here, and yeah, Celsius is equal to about 20 degrees. All right, so that seems reasonable to me for this equation. But when you get into industry and you're messing with some really low level programs with some complex formulas, you may want to be a little more scientific than what I just did. Seems reasonable. Um, you should probably punch in those numbers into a calculator and make sure that you're getting the same result on that calculator as the computer is, because sometimes you miss parentheses, sometimes it's doing the order of operations in a different order than you expect. For instance, here's an excellent science experiment. Watch this. Let's say I forget these parentheses, right? We know the value should be 20. All right, it's going to be happy here. I'm going to move the breakpoint to here. Let's run the debugger and watch what happens when I remove the parentheses. Remember, Celsius is equal to 20. This is saying Celsius is equal to 5.77. And the reason being that the computer follows PEMDAS, right? And it's going to do, let's see, PEMDAS, multiply, divide. It's going to do this first. Then it's going to take the result of that and do this part. Then it's going to take the result of that and then finally subtract. That is incorrect. Parentheses forces the computer to do this part first, right? Because P in PEMDAS is parentheses. We can always force the computer or the math operation to do an add or subtract first if we add these parentheses. Okay. All right, so that was an interesting little science experiment. What if we get rid of this dot zero, right? I was just telling you. Why do we need to put this dot zero? This formula says 5/9, not 9.0, and 0.0 is kind of silly, right? It's the same thing. Well, let's try it. All right, let's run the hit here. Remember, should be Celsius is equal to 20. If it 68 degrees Fahrenheit is 20. Hit step over here. Look, Celsius is 0. Well, that can't be. That's the freezing point of water. So again, what's happening is that integer divided by integer is 0 point something. It drops the point something, and now this is just 0. Right? So if we want to force this to return us a float or a double value, just add the point 0, and then the compiler's like, oh, they want a floating point value. My bad. All right. So that's why that's there. We understand that now. All right, let's keep going. So we should debug the file. All right, here we go. So the Celsius looks good. Celsius is equal to 20. Hit line 18. It should output all of this to the screen down below here in the output window. Yeah, 68 is equal to 20. That sounds right. Now here, 23. Well, let's do the opposite formula. Okay. And let's store whatever 20 degrees Celsius in this Fahrenheit formula is, and it should create a new variable called Fahrenheit 2 here and update and then write this value to it. Let's see what value it writes. 68. Perfect. And notice that this value and this value is equal. Therefore, we have two good formulas, um, two good lines of code, and we verified them. And then lastly, line 26 says, all right, well, let's print the string along with the value of Fahrenheit 2. Bada boom, bada bing, that's 68. We reached the end of our program. It terminates. Everybody's happy. Right. So that is chapter 2. And that's all we have time for today. I hope that everyone is finding these webinars / code reviews useful. Please continue to leave me feedback, either comment, like the video, email me, whatever. I really appreciate the feedback. It's what keeps me going and helps me make these videos better. Okay, so have a great rest of your week, and we'll meet again soon.